This video lesson is an introduction to polar graphing and polar coordinates. You should have received some polar graph paper to go along with this video lesson. If you did not receive it, then look for the link that goes with this assignment, and you can download a sheet of this graph paper. So to get into graphing with polar coordinates, suppose that you work in the control tower at an airport, and you're in charge of reading the radar screen, and notice that it has detected an airplane that's 2 miles from the airport at an angle of 60 degrees in standard position. Could you plot the plane's location relative to your location? Why don't you pause the video and give that a try? Then you can check your work with what I have. Okay, so we need to, I guess, decide where our location is, and I'll just plot a point right here. And now we know that this airplane is 2 miles from our present location, so that might, determine kind of like a circle around our point that has a radius of 2. And then if it is at an angle of 60 degrees in standard position, well, let's see, we know standard position is due east, so if we go about 60 degrees from due east, then I think we could maybe say that this airplane is at, I'll call it point A, right up here. I would say there's a very good chance that you found pretty much the same location that I did just following these instructions. They're actually pretty clear, and they point to the fact that we could actually plot points using a different coordinate system than the one that we grew up with in Algebra 1 and Algebra 2. Yes, in fact, you used what is called a polar system to plot this point. Let's take a look at what that involves. The polar coordinate system consists of 2 pieces. First of all, you start with a point that you call the pole. And that's typically thought of as kind of the same thing as our origin on a rectangular Cartesian system. And then we have just one axis on the polar system, and that is the horizontal axis that goes out in the 3 o'clock position. We call that the polar axis. When we plot a point, we simply map out, we go out at an angle, which we could call theta, an angle in standard position, and we go out the terminal side r units. Okay, and the coordinate of that point is r theta. Even though we usually use the theta first and then the r, we always write the r first and then theta. So get this in your notes here. It's nice to have the drawing to go with it. And we have the polar coordinate is r theta. R, of course, is the distance from the pole, and theta is your angle of rotation from the polar axis in standard position. Whoops, I misspelled standard. Let's put another D on there. Once you have this in your notes, let's move on to the next slide where we can get some practice using this system. Find your polar graph paper that you should have received from me, and why don't you pause the video and see if you can plot each of these points on one of your polar graphs. We can do the first one together. If we're looking at the point 4, 5 pi over 6 right up here, then we're actually going to use the 5 pi over 6 first. Okay, keep in mind each of these lines is 15 degrees apart, so 5 pi over 6 is pi over 6 units back from pi. So here's pi right here, so pi over 6 would be like 30 degrees back from pi. So we're looking right out here at 5 pi over 6, and we want to head in that direction 4 units. So we'll use these circles here, 1, 2, 3, 4. This looks like where we should be plotting point A, so we'll label that point A. All right. So do the same thing with the rest of these points and see if you get the same thing that I'm going to plot. Okay, check and see if you got the following for each of your points locations. So here is where I plotted each of my points. We had point A already. B, of course, has the negative angle, negative pi over 2, so we rotate clockwise down to this position, the negative 90, and out 3 units. Point C is might be the trickiest one. You had to find negative pi over 4, which is over here, but hopefully you notice that the R value is negative. And yes, what that means is we just want to head in the opposite direction that many units. So if we head out 5, 1, 2, 3, let's see, did I count that right? 1, 2, 3, 4, 5. Yes, there's where point C is in blue. All right. Yes, you might also notice that that's also where point E is, right? So the point negative 5, negative pi over 4, I'm sorry, point F, that should be point F for in red there. All right, so the point negative pi over 4, negative 5, negative pi over 4 is the same as positive 5, 3 pi over 4. All right, let's see, point D is kind of interesting because notice that its plot is the same place that the point 1, 0 would be in a rectangular system. But we have a 0 degree angle, a 0 radian angle, and we're just going out 1 unit. Point E is also kind of interesting, although I use 0, 7 pi over 2. It's basically in the same place that 0, 0 would also be in if you think about it. So, of course, if your R value is 0, you have to be at the pole. Now that you've done this little exercise, let's consider a few questions on the next slide. Is it possible for a point to have more than one pair of polar coordinates? Well, certainly we saw in our exercise that that would be a definite yes, right? I think our example was, right, we had negative 5, negative pi over 4, and that yielded the same point as positive 5, 3 pi over 4. And of course you can imagine there are actually infinite coordinates, polar coordinates for that same point. We can just keep using coterminal angles to 3 pi over 4 and we will still have the same point. Now, what about in a rectangular system? Is it possible for a point to have more than one pair of Cartesian xy coordinates? If you think about it, that's really not going to happen. Okay, so these two systems are a little different in this basic way that there's only one pair of coordinates for any point in the Cartesian plane, but there can be infinite coordinates for most any point in the polar plane. All right, last question. I thought this would be a good review. Do you remember why we call the rectangular system the Cartesian coordinate system? Hopefully you had a little discussion with your Algebra 1 teacher or even Algebra 2 teacher about why we name it that. It is named after a person, which is why we usually capitalize the word Cartesian, right? It was the philosopher René, I'll spell it out, René Descartes. Of course, it's spelled Descartes. Okay, he was the one who had the ingenious idea that it might be possible to represent a geometric concept, like a point, using numbers. And of course, his discovery or his invention, if you want to call it, led to opening math up so much because now we could actually tie algebra into geometry and represent shapes, geometric shapes like lines and circles using variables. Okay, so on the homework, when you do the homework assignment for this lesson, you are going to be asked to do some conversions. So I want you to consider what would the Cartesian coordinates be for the polar point 2 pi over 3? And if you really think about it, you have actually answered this problem before. Let's just sketch this out. If we see where is this point 2 pi over 3, you could use your polar graph paper if you like, but I'm just going to sketch it out here. When I draw it like this, hopefully you recognize this problem. We've seen problems in our book like this, right, where you had to figure out what are the x and y coordinates of this point. That's all we're doing here. So give that a shot and see if you get what I get. You should be able to do this without a calculator. Okay, check and see if you got this. All right, so if we just, I went ahead and drew in a little right triangle here. If you want to, you can do that and label your x and your y sides of the triangle, but we know that the cosine of the angle is going to be x over 2, or even better, we just need to multiply, right, the cosine of our angle by our value r. We've seen this before. So we just get 1 for the x coordinate, and then we do the same thing with the y, just our r times the sine of our angle, and we get y equal to root 3. So the formulas here, or that we were using, or the equations we were using, was just that x always equals r times the cosine of theta, and y always equals r times the sine of theta. This is nothing new to you. Okay, let's see how you do converting the other way now. Go ahead and figure out what the polar coordinates would be for the rectangular point -2, 3. If you want to draw that out, it's not a bad idea. Let's see, -2, 3, -2, and 1, 2, 3. So we're right here for our x and our y. We could draw in our hypotenuse of our right triangle. We got -2 here, 3 here. Of course, we're trying to figure out what r is, and we're also trying to figure out, keep in mind, we're trying to figure out this angle, theta. All right, so go ahead and see what you get for r and theta. I will let you use your calculator to get these values. All right, so check and see if you got what I got here. All right, so the first thing I did was figure out what r was just using the Pythagorean theorem, right? That I know r squared equals x squared plus y squared, so we get r squared is 13, therefore r is root 13. And now I decided to use, though you didn't have to do this, but I decided to use the tangent function to help me figure out what theta was. Since they gave me x and y, that seems to be the logical choice. So tangent of theta would be 3 divided by -2. So I take the inverse tangent of -3/2, and I get theta to be -0.983. So there we go, right? Root 13, comma, -0.983. I'm hoping that you are thinking maybe this isn't quite right, because we know that -0.983 is not an angle that's in the second quadrant, is it? No, in fact, the calculator gave me back this angle down here in the fourth quadrant. All right, let me draw that in. This is where -0.983 is. So my answer is not correct. Okay, the root 13 might be correct, but not the -0.983. Although, if I did this, then I think my answer would be correct, right? Just make sure it's going the opposite direction. But what's a way that I could give this answer so that I could let r just be the positive root 13? And this is another reason why I like to use the tangent function, right? Remember when we were solving trig equations, we learned that if you don't get the right angle with inverse tangent, all you have to do is add pi to it. And if we do that, then we will have our angle of 2.159, which is in the second quadrant. So either of these two answers right here would be correct for the polar coordinates of the point -2, 3. Okay, so we now have 4 equations that are really helpful for us when we want to do some conversion, either from Cartesian to polar or from polar to Cartesian. All right. I have made this drawing here to kind of set the scene. As you can see, it has representations of both types of coordinate systems. We've got x and y represented here, and then we have r and theta. These are all quantities that we are very familiar with. So our two equations that take us from polar to Cartesian, those would be the first ones we used. That's what we were doing in our first example, and that was x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. All right, very familiar equations, but they will help us do that conversion, right? If we know what r and theta are, we can just plug them right in to these two equations and determine x and y. And then to go from Cartesian back to polar, we have our two equations that the tangent of theta is simply equal to y over x. And we also know that r squared will equal x squared plus y squared. If you want to do the, r is equal to the square root of that, that's fine too. But I usually just go with the Pythagorean theorem. What you're going to see as we move along through pre-calculus and even into calculus is that there are many times when we might really want to be in a Cartesian system, but there's also going to be times when looking at something from a polar standpoint will be more advantageous. So these four equations will be very, very useful. Okay, you should know them by heart very soon or very quickly, or just keep them in mind. So when you need to pull them out, you can just say, oh yeah, I know that x equals r cosine theta, y equals r sine theta, and I know that the tangent of theta equals y over x, and that r squared is equal to x squared plus y squared. These four equations are all we need to be able to look at new phenomena from two perspectives. And you're going to see this in the very next section when we look at complex numbers. We're going to now take a look at graphing some simple polar equations. So what do you think the graph of the polar equation r equals 4 would look like? And think about it from this perspective. You just want to plot all the points that have an r coordinate of 4. It doesn't really matter what theta is, you just have to make sure that r is 4. So what would that graph look like? Why don't you plot, say, 3, 5, 7 points that have an r value of 4, and then see if you can sketch in the graph. Well, hopefully, as you were going along, you started to see that all the points you were plotting were ending up on this circle here, right? If you're going to have an r value of 4, then you have to be on the circle. So this is actually one of the simpler polar graphs that you can do. It's just a circle of radius 4. Now what about the polar equation r equals negative 4? Would that be any different than what you just plotted? Certainly not, right? Because every one of these places that we plotted before that had an r value of 4 could also have been a place where we had an r value of negative 4. So we basically get the same graph no matter whether the r is positive or negative. Now I didn't use polar graph paper to plot this line here, but and hopefully you're already recognizing this is just the line y equals x. But if this was in a polar plane, what would the equation of this line be? You might want to think about every point on this line and what do they all have in common in terms of their polar coordinates, either r or theta. Well, if you figured out that every one of these points has a theta value that's equal to pi over 4 or 45 degrees, then you're there. You have it. All we have to write is theta equal to pi over 4. That is the polar equation for this line. It's basically saying we don't care what r is, but make sure that your theta, or your angle, is pi over 4. So this is a very simple equation. It's a simple equation in Cartesian as well, but it's also a simple equation in polar. And generally, most graphs that revolve around the pole or go through the pole tend to have a fairly simple equation in polar. We will get more practice with graphing polar equations later, but at this point, if you would like to get ahead, you are definitely ready to do the first assignment off the assignment sheet for section 8.5.